And welcome to our final video for HL Nuclear Physics and IB, where we're going to talk about radioactive decay law. Now, I presented this when we talked about topic 7.2. We talked about radioactive decay, and I actually showed everybody the actual decay law and understanding that the definition of radioactive decay is that the rate of radioactive decay is exponential and it's proportional to the total number of nuclei. As you can see in this diagram, I'll have my original sample has 100% radioactive nuclei, and after a certain amount of time, only half those nuclei remain. The rest of them, which is undergo a random spontaneous decay process, I can't predict exactly which ones are going to decay, but I can only say that there's a probability that after a certain amount of time, this time over here, that half of the atoms would undergo that decay. And that exact same amount of time, if it passes again, half of those atoms will undergo decay. Again, I can't predict exactly which atoms are decaying. I can just say there's a probability that half of these atoms will decay over a certain amount of time, and that time is called my half-life, the half-life time. So we've learned a lot about this in topic 7. Now we're just going to apply some exponential math in the HL to be able to do some calculations where we're able to calculate the amount of radioactive substance halfway through, not actually in a half-life, but maybe partially there. I can tell you exactly how many atoms of a substance will remain at any point in time if I use this function. If I just understand half-life like I did in the SL section, I can only go by half-lives. But now with these functions I'm about to show, you can calculate the total amount by actually modeling this graph. Okay, so in order to move forward, we need to remember this formula, that the actual amount of atoms remaining will follow this exponential function as long as I know the total amount to begin with, and I know something called lambda, which is my proportionality constant or my decay constant, and that tells us the probability of radioactive decay. So if I see that lambda constant for a radioactive substance is very high, that means that there's a high probability it's going to decay, and it would decay quickly. Okay, and T represents the total time that the sample is decaying. Again, according to the rate law, the rate of radioactive decay is proportional to the total number of atoms present. That's why the slope is steepest over here. And the activity, the radioactivity of the sample, is the product of the proportionality constant, or that probability, times the total number of atoms there. So as the total number of atoms decay, the radioactivity goes down proportionally. Okay, and this entire formula can be converted into radioactivity by multiplying that lambda, that decay constant, times the number of atoms present. Okay, so my initial radioactivity is lambda times my initial radioactive atoms present. Okay, and then that'll undergo a decay similar to this, and I can find out the radioactivity at any point in time using this formula. So you have this formula in your data booklet, you have that formula in your data booklet. It's very important that you know what lambda is, it's the probability, and it's very important that you know what the rate law is for radioactive decay. Often, there are many different ways of measuring or describing radioactivity, but in IB, they'll often talk about becquerels. Now, becquerels is a unit of measure for radioactivity. When you use a Geiger counter, it makes those clicks, and every click is a radioactive decay that's detected. So the number of clicks per second is measured in becquerels. So 1 click in 1 second is 1 becquerel. 10 clicks in 1 second would be 10 becquerel. Okay, and that's the simplest way of measuring radioactivity. Okay, so all radioactive substances, if atoms will decay per second, if 10 atoms decay in 1 second, the becquerel count would be 10 becquerel. Okay, now remember, when we're doing questions, and I'll show you at the end of this lesson, that we need to subtract the background radiation. We have background radiation due to the sun. The sun is constantly bombarding us with radioactive particles, and so if I have a detector out, it'll be clicking even if there's no radioactive substance around because there's background radiation. So we'll have to deal with that when we get to that in these problems. On the left here, you'll see a table of just common radioactive substances: uranium-238, plutonium, carbon-14. Here's their half-lives, and here is their corresponding decay constants. Okay, the longer the half-life, the less likely it's going to decay, so my decay constant, the probability, is very low. On the other hand, take a look at this. Lithium-8, it has a very short half-life, meaning it'll have a very large decay constant. These ones are even shorter in time, okay, and it'll have an even faster decay constant. Okay, so if I was to graph the activity, this should say activity on this side. Let's write that in. Okay, so if I was to graph the activity over time, okay, what I would see for uranium-238, the graph would be less steep because it has a longer half-life and a smaller decay constant. But for a substance that has a very large decay constant and a shorter half-time, like plutonium, it would be quite steep to begin with. Okay, it would decay much quicker. So that's an important qualitative thing to know if you're going to be talking about that on a multiple choice question on IB. So let's solve some example problems. Okay, how can we put these equations to the work? Okay, so arsenic 81 has a half-life of 33 seconds. A freshly prepared radioactive sample contains 100 grams of arsenic 81. Calculate the amount of time needed for the sample to decay until only 6.25 grams of arsenic 81 is left. Okay, what I like to do is I like to create a table of values on the left-hand side just to keep myself organized. The initial amount, okay, it could be number of atoms or it can be mass. The initial amount of arsenic 81 is 100 grams. It has a half-life of 33 seconds. The final amount is 6.25 seconds. We're trying to calculate the time, and we don't know the probability constant. We don't know that decay constant here. So the first step would probably be for us to use this equation, and in order to find the time, I first need to find my decay constant. So I can do so using the half-life. If I know the half-life, there's a nifty trick I can use to be able to calculate lambda. And it's important that you'll take some notes on this because this often appears on exams. So if I plugged in this, and for n at the half-life, n will be equal to 1/2 NO. Okay, that's at the half-life, the time taken for the substance to decay by half. All right. Then the NOs are going to cancel out. I'll be left with 1/2 is equal to E negative lambda T 1/2. That's the half-life time. And then if I do the math with my exponentials here, I can do the algebra and I'll get to this. Now this is a very important formula that you should memorize. ln2 divided by the half-life of a substance is the decay constant. Vice versa, if I take ln2 divided by the decay constant, I can find the half-life. That's a very useful identity. All right, so ln2 divided by 33 seconds is equal to my decay constant, which is going to be equal to 0.021 per second. That's the units for decay constant. Now that I know lambda, I can now plug it into the formula, and I can then calculate following everything here. Okay, 6.25 grams is what is remaining. 100 grams is what we started with. I plug these values in, do my algebra, as you can see over here, and that would tell me 132 seconds is the time it would take. Now, I could have done this in my head based on the numbers because there's a total of 4 half-lives to get down to 6.25 grams. So 4 times 33 could have given me the same answer. Now, that's just because I chose something simple, but in the IB, they're not going to give you something that is round like that. You'll have to apply this equation. All right, for example 2, let's look at something more radioactive like lithium-8. A sample of lithium-8 was freshly prepared in the lab with natural background radiation of 20 becquerels. Now here's where I'm talking about background radiation. Okay, the activity of the sample was initially measured to have 640 becquerels using a Geiger counter. Calculate the time taken for the sample to decay to an activity of 40 becquerels in the lab. Well, my sensor, my Geiger counter, doesn't know about background radiation. So the first thing I have to do is I have to subtract the background radiation from my samples. Okay, so 640 minus 20, well, that's my actual initial activity. And then 40 minus 20, that's my final activity, 20 becquerel. Okay, my decay constant is 0.825 per second. I found that in this table over here. I used that one. Okay, and all right, to calculate the time, I'm going to plug it into this formula. So this is the formula I have in my data booklet. The radioactivity is equal to lambda NO. Well, that lambda NO is my initial radioactivity. So I just move that into here. Okay, and then that's my final activity, my initial activity, lambda, which we have over here. I can calculate the time by doing the algebra. Okay, so the time taken to decay all the way down is 4.16 seconds. This is a dangerous, dangerous substance because it has a very, very, very short half-life. It would be super radioactive. You would have to work with it behind a lot of protective material. All right, so to finish this, a very helpful tip when you are working with radioactive half-lives is this formula here. So I can calculate the decay constant by taking ln2 divided by t1 half. And sometimes what they do is they show you a graph in the exam, and then you have to use data from the graph. Well, if I can determine the half-life from the graph, and I know that number, I can plug that into here to calculate the decay constant and use it in subsequent calculations. That's it. Good luck with doing your practice problems.